Right, redox chemistry, topic 9. This is what we're going to be looking at. Again, quite a lot to get through in this section. Start by just kind of recapping what ionic equations are all about. And if we look at these ionic substances in solution, then what they're actually existing as is ions. They're dissolving up and the ions are becoming released. So if we expand what we've got in there, hopefully you can see that the sodium ions and the chloride ions essentially aren't really making any change, and we would describe those as spectator ions. And if we wanted to write an ionic equation for actually the chemistry that's taking place, well, that is it. H plus with OH minus goes to H2O, and that for any acid alkali reaction, that's going to be the overall change, which is why they very often have similar enthalpy change values, because it's the same H plus plus OH minus going to H2O. Another example down here, this time we're forming an ionic solid. So again, if I expand this up, I've got Ag plus, NO3 minus, K plus, I minus. It's giving me AgI as a solid plus K plus plus NO3 minus, and they're not really up to much. So my ionic equation, the only chemistry that's happening, is left there with the Ag plus plus I minus. Right, so oxidation and reduction. Maybe talked about oxidation as gaining of oxygen, and sure enough, I mean that's obvious here. Magnesium gains oxygen to form magnesium oxide. It is an oxidation. However, we've got to get familiar with more subtle changes, such example here. Right, this is a redox reaction. It's an oxidation and a reduction taking place, and we can expand our definition beyond gain of oxygen, loss of hydrogen, or loss of oxygen, gain of hydrogen, to oxidation being loss of electrons and also an increase in oxidation state. Right, so these are the things to look for an oxidation, and the opposite would be our reduction. So keeping in mind those definitions of an oxidation, maybe we can try and explain what's going on if we break this down into the ionic changes. So if I write this out again as an ionic equation, then my sulfate spectator ion. But what changes have I got going on? Well, the zinc is becoming Zn2 plus, and the copper 2 plus is becoming copper. And I can balance this up by showing what the electrons are doing, like that. And that means this is losing electrons. Right? It has been oxidation is lost. It has been oxidized. This has gained electrons, so the Cu2 plus has been reduced. And if we think in terms of their oxidation numbers, which we'll come on to in a moment again, the oxidation number of that is 0, that's plus 2, that's gone up. This is plus 2, that is 0, that's gone down. Now in this reaction as well as saying what has been oxidized and what has been reduced, we can identify an oxidizing agent, something which causes another substance to be oxidized. And we can identify a reducing agent, something which causes another substance to be reduced. So because my zinc is causing the copper ions to be reduced, we can describe it as a reducing agent. And whilst that zinc has been losing electrons, it itself has been oxidized. Right, so some definitions there to be familiar with. So going back to this idea of oxidation states, so we're taking this to be we're pretending, whatever it is, that it's got some ionic character to it, right? No matter if it's covalent, ionic, whatever. And it's the charge that your atom of interest would have. Now these rules of thumb here are important for helping you work out unknown oxidation state. So any element is uncombined, oxidation state 0. Group 1 metals, well, they tend to form, because they lose one outer electron, +1 ion. So their expected oxidation state is +1. Similarly, magnesium, calcium, they're going to be losing 2 electrons. It's hard to think of any compounds where it's not like MgCl2, MgO, MgBr2, where we're not dealing with like Mg2+. So the oxidation state there is +2. Hydrogen, usually, nearly all examples, you can see an exception there, it's going to be +1. Oxygen, again, nearly always -2, there is an exception there. And chlorine and fluorine, particularly fluorine, is always going to be -1. Chlorine can change, but more often than not, we can take that to be -1 in a compound. It might be different, particularly if it's bonded to something like oxygen. So, here are some examples that you might like to have a go at yourself. You can see one of the elements has been underlined, and you need to try and work out what the oxidation number of that element is. So if we were to take the first one, then our H is +1, we don't know N. Oxygen, we've said, is very normally always -2, there's 3 of them, and because overall the thing is neutral, it's got to be equal to 0. So I can solve that for my N, which means that my N is equal to, so that goes over there, +5, +6, +5. Chromium in here, well, the potassium's going to be +1, and I've got 2 of those. I don't know what my chromium is. 2 of those though. And I've got 7 oxygens, -2. And again, that overall has to be equal to 0. So if I solve that, each of the chromiums is going to be in a +6 state. Phosphorus here is going to be -3. Bromine, it's an element, it's going to be 0. The aluminium in there, +1, plus my aluminium, +4, lots of +1, equals to 0, which means my aluminium is going to be, that becomes, right, so because this is, sorry, my mistake, because this is a metal hydride, then our rule down here is that the H has to be a -1. So that should be -1, right, -1, which means I'm going to end up with a positive value for my metal, which makes more sense. So that's -1, that's 4, so the aluminium there is going to be +3. This one, got manganese, I've got 4 oxygens, and this time the thing has an overall charge of -1. Solve it, the manganese is going to be +7. Keep working through these, PO43 minus, then I'm looking at PB plus 4 times -2 equal to -3, which means my lead has to be +5. Now if I've got a recognizable compound ion, I kind of treat that intact. So that's sulfate. We know that sulfate is combining power 2, SO4 2-, which means my lead is going to be 2+, so its oxidation state is +2. Similarly, the aluminium here, I've got 2 aluminiums and I've got 3 lots of -2 from the carbonate, which means my aluminium must be in +3. Cool. Transition metals. Now, something unusual about them, which helps them act as good catalysts, is that they can show a variety of oxidation states. And you can see a list of common oxidation states in your data booklet. But it means that to help people understand which oxidation state we're referring to, then we use these Roman numerals. So the 1, like that, means that we're dealing with an oxidation state of +1. So the formula, if it's Fe+, I would need 2 of them to go with my O2-. Something like CuCl2, and this there's 2 Cl minuses there. That must be the copper 2 I'm dealing with, copper 2 chloride. Titanium, here it's going to have to be in a +6 state, titanium 6, like that. Chromium 6 fluoride, well, that's going to look like that, so I've got 6 F minuses, that's going to make that the 6 plus. And this one is called vanadium pentoxide, vanadium 5 oxide, because again, if you work that out, the oxidation state must be +5. So something like sodium is always Na+, something like magnesium always Mg2+, but because we have relatively small differences in successive ionization energies, copper can lose 1, copper can lose 2. Right, you could have copper plus, copper 2 plus. Vanadium, you can see there, can go right through to 5 plus. Right, there's some more examples to have a look through. So let's put some of these ideas together and try and explore these reactions a little bit, see what's going on. So if I break this up, I can see my potassium ions, nitrate ions aren't going to be doing very much in this reaction. So what changes have I got? Well, I've got Ag plus I minus going to AgI solid. Am I seeing any changes in oxidation numbers? No. This is still Ag plus here. That's Ag plus there in the ionic solid. I minus, I minus. So this actually isn't a redox reaction. There's no changes in terms of oxidation states. Down here though, if I expand this again as we saw in a previous slide, I've got those two changes where my Zn was giving me Zn2 plus 2 electrons, and my copper ions were picking up electrons and forming copper. And you can see that that is going from 0 to +2, that's going from +2 to 0. That is an oxidation. This is a reduction. This one, a little bit more complicated looking, but we can still just pick out some of the key elements. How are they changing? Well, tin there is 0. There it's going to be at +2. The chromium there we saw in a previous slide is going to be at +6, and there it's at +3. So the tin has clearly been oxidized, and the chromium has been reduced, which means, if we wanted to assign names, this, because it's caused a reduction, is called a reducing agent. This, because it's caused an oxidation, is called an oxidizing agent. At the end, you can see a specific example of something called a disproportionation, where one atom is both oxidized and reduced. So you see it's chlorine here, element starts off as 0, goes to -1 in this state, in this this ion, and then over here it's also at +1, so we call that a disproportionation. Right, so earlier on in the course you'll have learned how to balance relatively straightforward equations. Some of these redox equations can be a bit trickier to build up and to balance, and so this page here takes you through the steps that I would go through. So the first thing, if we've got trying to get these two half equations, as we call them, so these are the two half equations that are going on. If I take the tin one and then the chromium one separately, I can build up two half equations. And first thing to do is to look at the kind of non-oxygen element. What's that doing? Do I have enough on both sides? For the tin, that's fine. For the chromium, looking at that, I'm going to need 2 there to balance that. Then if I've got any oxygens, I can add in water to balance those up. Then for the H's that I've just added in, I've got to add in H pluses to balance those up. Then I check through my charges and I can add in electrons to balance the charges on both sides of the equation. And then I'm going to have to scale one of them up, maybe both sometimes, but usually just one, so that when I add them together, my electrons cancel out. So let's look at that in a worked example. So typical paper 1 question. It says insert coefficients to balance the following equation. So I'm going to break that down into two half equations. MnO4 minus going to Mn2 plus, and I've got SO2 going to SO4 2 minus. So if we start with this one, manganeses are okay, but I'm going to need some oxygens on the right, so I'm going to do that by adding in some water. Mn2 plus 4H2O. Now I need to sort out those H's that I've just added in, and I'm going to do that by adding in some H pluses, like that, to the left. And now I need to look at the charges, and I can see that this side is 7 plus, this side is 2 plus, so I'm going to need 5 electrons there to balance that. Over here, sulfurs are okay, but I've not got enough oxygens on this side, so I'm going to add in 2 waters to add in the extra oxygens I need. Then I'm going to have to add in some H pluses here to balance out, the H's that I've added in there. Now I look at my charges, that's 0 over there. Over here it's plus 2, so I'm going to need to add in 2 electrons. Now I want to be able to combine these together so that when I add them together the electrons cancel. Now unfortunately it's not going to be that easy. I've got a 5 and a 2, so I'm going to have to scale that one up. I'm going to multiply this one right through by 2, so it becomes 2MnO4 minus plus 16H plus 10E minus gives me 2Mn2 plus 8H2O, and this one here is going to be multiplied through by 5, so that I end up with 5SO2 plus 10H2O goes to 5SO4 2 minus plus 20H plus 10E minus. Now I'm going to add those together, and maybe we'll just write it out. So adding them together I end up with 2MnO4 minus plus 16H plus 10E minus plus 5SO2 plus 10H2O gives me 2Mn2 plus 8H2O plus 5SO4 2 minus, I'm running out of space, oh, got right on there, plus 2OH, oh sorry, that was 20H plus 10E minus. So my electrons go. Can I cancel down any H pluses? Yep, I can get rid of all of those to leave me with 4 just there. And I think that would then give me 2 and 5. My water, so I can cancel these down as well. That becomes 2, they all disappear. 2, 2, 5, and 4. Right, so something that you would never be able to balance without going through that method. Right, it's a redox titration question. So it starts off the same idea. You need to build an equation, and then you can do your stoichiometry calculation on it. Right, so we're going to have to build up 2 balanced half equations and then add them together to give us our full equation. I'm guessing I'm going to run out of space again here, but let's see. So balancing this one, ions are okay. We need to be, well, that's okay as it is. This one here we've already seen on a previous slide, so I'll move through it relatively swiftly. The manganeses are okay. We need to balance the oxygens with water. I've got to then balance the H's with H pluses, and then looking at the charges, I've got plus 2 plus 7, that's got to have 5 electrons on it. So I have to multiply this one through by 5 before I add them, and then I can add them together. So just as a side point, you notice this has H pluses in it. This is often why we use acidified solutions of potassium permanganate, because it needs H pluses in there for its reactions to occur. So when you get potassium permanganate in your chemistry labs, it's often acidified because it needs these H pluses to react. Anyway, so let's multiply this through by 5 and then add the two equations together, which is going to give me 5Fe2 plus 8H plus those electrons, which are going to disappear, plus MnO4 minus goes to 5Fe3 plus the 5 electrons that will disappear, plus Mn2 plus 4H2O. Now the important ratio, so now we're kind of just in a stoichiometry calculation, because I've been told I've got 0.01 molar of that, and I'm using 35.6 centimeters cubed. So I can convert this to a number of moles. That's going to be N equals CV, so it's going to be 0.01 times 35.6 over 1,000, which is 3.56 times 10 to the minus 4. Then mole ratio is 1 to 5. So that's going to give me 5 times the number of moles of iron, which is 1.78 times 10 to the minus 3. Number of moles of iron is equal to mass divided by mass of 1 mole, which means the mass of iron that I've got in my reaction is 0.0994 grams, and then I need that as a percentage of that, so 0.0994 divided by 0.725 times 100 is going to give me 13.7%. Right, reactivity series of metals. Well, we saw zinc earlier reacting with copper sulfate, and zinc is a stronger reducing agent than the copper, and so it was causing the copper ions to be reduced. But we can use this reactivity series to predict what reactions are going to occur. So zinc's going to be quite high up in our series. It's only there. It's a relatively reactive metal. So reactive metals, you've seen some of these added to water. Less reactive metals down here. Now we can use this rule that a more reactive metal will displace a less reactive metal from a solution of its salts. So taking that, it means that our iron, which is here, and copper, which is here, so copper's higher up the series, it's more reactive, it's going to be taking the place of that, and we're going to end up with iron sulfate and copper being produced. So what would you observe? What would you see? You'd see that kind of reddish brown solid forming. Here, silver, which is there. Will that react with magnesium ions in magnesium nitrate? No. No reaction, because the magnesium is higher up the series. Right, biochemical oxygen demand. So, within water, there may well be some organic matter, and that organic matter, for the water to become clean, needs to be broken down. Bacteria are going to be the ones to break that down, and they require oxygen, assuming they're aerobic bacteria, to break it down. So they need a certain amount of oxygen to break it down. So if we've got lots and lots of organic matter, there was lots of pollution in there, there is a large biological oxygen demand, because more oxygen is needed by the bacteria to break it down. Now we can measure this, BOD, usually over a period of 5 days at a set temperature, and we can work out how much oxygen is used in that process to work out its BOD. But to work out the amount of oxygen dissolved in a sample of water, we need a special method, and that method that we're going to look at here is called the Winkler method. And a few steps to it. You start by adding in some manganese sulfate, and that kind of traps the oxygen. So it's important that when we're collecting our sample, we're not shaking it about or unnecessarily aerating it. So we get our manganese sulfate in, traps the oxygen, and then we're going to add in some potassium iodide, and that ends up with some iodine produced, and then the iodine that's produced is titrated against sodium thiosulfate, and from that titration we can work back and see how many moles of oxygen we were starting with in that sample. Now the shortcut kind of ratio is that. If we look at this question here, maybe I'll go through it step by step without using that shortcut so you can see where that ratio is coming from. So we've got a thiosulfate, and the thiosulfate equation, if you refer back to that one, you can see it's 2 thiosulfates, 2S2O3, 2 minus, with, sorry, 1 iodine, like that. So, taking these numbers then that we've got 8.5 centimeters cubed, and we've got 0.1 molar. Our number of moles of that is going to be concentration times volume, which is 8.5 times 10 to the minus 4. 2 to 1 ratio, which means my iodine is going to be 4.25 times 10 to the minus 4. And then, working that back through, I can see I've got a relationship between manganese dioxide and the iodine, and that is a 1-to-1 ratio, so 4.25 times 10 to the minus 4 is going to be 4.25 times 10 to the minus 4 of the manganese dioxide. And then, so that's my first thing, second thing, third thing, I've got my oxygen and manganese dioxide relationship, and that was a 2-to-1. So if this is 4.25 times 10 to the minus 4, then the oxygen is going to be half that, which is 2.125 times 10 to the minus 4. And you can see maybe there with those two halvings we've got that 1-to-4 ratio. And that number of moles of oxygen is in 250 centimeters cubed. That's my sample size. So then working that out as a concentration is N over V, which means my concentration is going to be 8.5 times 10 to the minus 4 moles per decimeter cubed. Right, that's what we've covered.